So the thing that we have to cover here is, again, the reactivity of the benzylic carbon. That's what we were just talking about a second ago. We saw that you can do more extreme oxidations of benzylic carbons than of normal carbons. We could oxidize them all the way to carboxylic acids and cleave carbon sigma bonds. Something else that you can do is that they're very reactive for radical mechanisms. So we need to, it looks like that was an important thing for your instructor. So we need to go through the radical mechanisms. And it really is just a review. So all we need to know is that this is reactive for a radical mechanism. So to go over the mechanism, what would happen first here?
First, the BR would break and form two lipids. Don't you need light and heat?
Here we're using heat. You're right, light would also work. So in the textbook they mentioned heat or light allows attack by chlorine or bromine. So, and what step do we need the heat or the light for? We need it for this step. This is the hard step. This is what we call the initiation step. We know this is a symbol for light. That's our initiation step. What would happen then?
The radical Br would steal an H.
From?
The benzylic carbon.
Yeah, from the benzylic carbon. Now, if it has a choice, it's going to take it from the benzylic carbon, not from the benzene itself. And remember that with a radical mechanism, this is the way we draw the mechanism with these single-headed arrows. This is propagation step 1. Let's stop and talk about this for a second. Normally, primary radicals would not be very happy to form. Why is this particularly easy?
Because of the benzylic and the resonance bonds that can go through.
That's right, and it would be a good exercise to draw those resonance structures. For example, there's a resonance structure where the unpaired electron is on this carbon. There's another resonance structure where the unpaired electron is on this carbon. There's another resonance structure where it's on this carbon. Well, to save time, we won't draw all of those, but you should know that there are resonance structures that are spreading out the unpaired electron. That's the reason why the bromine prefers to take the hydrogen from the benzylic carbon, not from other carbons. But we won't go through that. Instead, what's going to be the next step?
The radical from the benzylic is going to break a new Br-Br bond.
Right. That's propagation step 2. And then what?
Then we return to.
That's right. Well, the best answer is then we can take this bromine radical and do another propagation step 1. The product from this, remember why this is called a chain mechanism. The product from this step can do another propagation step 1, and we're going to do billions of chain reactions before we do any termination steps. In fact, at this point in the course, we almost never draw termination steps. So this is all the mechanism that we would need. This shows the basic mechanism, and here's our key product. So the key thing is, if you don't want to go through the whole mechanism, the key thing is put the halogen on the benzylic carbon. Put the halogen on the benzylic carbon. Just like when we were working with potassium permanganate and the sodium dichromate, the key was oxidize the benzylic carbon. So let's draw the product here. I guess to save time, we won't do the mechanism. Let's just draw the product. Now we have a regiochemistry problem. We have to decide which of these 3 carbons is going to be most reactive.
The more substituted.
Now, what matters here is it's the benzylic carbon. So, in fact, even if there was a tertiary here, I think we would still pick the benzylic carbon. Because remember that resonance is usually more important than other effects.
Okay.
So, the only important product to draw here is this one. We shouldn't bother putting the chlorine on any of the other carbons. The resonance stabilization is the most important. We didn't go through the whole mechanism, but we know that the key step is when we're going to form this intermediate. Well, this unpaired electron would much rather be here where it's resonance stabilized than anybody else, because here it's stabilized by 3 other resonance structures. So the key thing here is the regiochemistry, if you don't want to go through the whole mechanism. So should we actually go through that synthesis they talked about? That was an interesting synthesis.
Yeah.
Okay. So let me take a look at, oh, I guess I have it here. So they're asking us to do this synthesis. Well, the first logical thing to do is to get a ethyl substituent on. So how could we get an ethyl substituent on the benzene?
Acylation.
Alkylation or acylation.
Right. What did they use? Did they use an acylation or an alkylation here?
They didn't use it, they just started off with it because.
Oh, they said they were allowed to do that?
No, they did. They did alkylation.
Alkylation? Okay. Alkylation is acceptable here because with only a 2-carbon chain, we don't need to worry about rearrangements. And I guess they just didn't worry about the over-alkylation issue, but we don't need to worry about rearrangements. So they put on the 2-carbon chain. Now the difficulty is to get a bromine over here. Now, would this work? Why can't we just do this? What's this going to give us?
That will play on the benzylic.
Okay. Well, that's still a good step. I think that's what they did next.
Yeah, he started with the methyl community, but they didn't start with anything. It was just a benzyne.
Now, it's important to realize we're not done yet because the bromine is not in the right place. Now, what we need to do here is we basically need to shift a functional group to the adjacent carbon. We need a trick for shifting a functional group to an adjacent carbon. Another way of putting it is, notice we need to defunctionalize this carbon and functionalize the adjacent carbon. Defunctionalize this carbon and functionalize the adjacent carbon. Well, there's a synthetic strategy for doing that. We should have talked about this previously. I don't think I ever spelled this out. But forming double bonds and then adding to them is a great way to shift a functional group from one place to another. Because when we form the double bond, it's going to be between these 2 carbons. And then we know that we can use all of those electrophilic addition reactions we learned in the first semester, either Markovnikov or anti-Markovnikov, to put the functional group where we want it. So the next step, did they do an elimination next? That's what I think. Okay, so what would be a good way to do the elimination here?
Aldehyde.
Yep, that would work. What type of mechanism would that give us?
E2.
It doesn't matter that they used NBS instead of BR2.
Oh, did they?
Yeah.
Well, we know that that's a good way to do radical halogenations, although we usually did that for allylic halogenations. Let's see, what do they do in the book here? In the book, they didn't mention that benzylic halogenations need NBS, so I think you would get full credit if you did it either way. But if they used NBS, I suppose that would also be acceptable. When do you definitely need NBS for allylic radical halogenations? For the benzylic halogenations, they didn't specifically talk about NBS in the book, but if they use that in the answer key, I guess that's an acceptable way to do that too. The main purpose of using NBS is to prevent ourselves from just doing an electrophilic addition to the double bond. But I don't think that would be an issue here because these are not very reactive double bonds because they're aromatic, so I don't think we need NBS here. All right, in any case, we did our E2 reaction here, and now we're almost done. What would we do now?
HBr in RO. Yeah.
Why can't we just do this?
Because that's going to add a Br on the more substituted.
This was the Markovnikov addition. So you're right, they really are reviewing a lot of reactions from the end of the last term. We saw this would be Markovnikov because it would put the carbocation on the more substituted. But we learned last term a way to do anti-Markovnikov additions of halogens. Remember, we called these peroxides. Peroxides are good radical initiators, so we can use this peroxide as a radical initiator. And we learned last term that this is an anti-Markovnikov. We could go through the mechanism and see this is anti-Markovnikov. This is the synthesis they used? Okay. Well, now that the final's coming up, you can expect that the instructor might find it pleasing to try to test some reactions from the previous term, putting things together here.